This is Karen Smith, and we're talking about operations on polynomials today. And so polynomials are made up of terms, factors, and operations. You've seen it before, okay? We call them expressions so far. And so what's going on is this is like the same type of thing you've been doing in a different context, okay? A polynomial basically is just an algebraic expression, okay? It's got one or more terms. Each term individually is called a monomial, okay? Mon meaning one, single, okay? And nomial just meaning parts, okay? It's got these pieces, so monomial, okay? And so a monomial would be this A here on the left side of your screen here. This guy here is a monomial because it's a single term. Now, terms are separated by addition and subtraction, or I should say addition or subtraction. Remember that factors are separated with multiplication, okay? But we're talking about terms when we're trying to decide if a polynomial is a monomial, a binomial, trinomial, or just larger. And so we're looking at the addition and subtraction in the problem. So for example here, I'm continuing on the top right, the excerpt of your textbook. A binomial would be a two-term polynomial, okay? And so we're looking for the addition, right? The terms are separated by, here's addition, okay? So the first term in this example, x squared plus 1, by the way, if you're wondering where I am, I'm looking at this guy, x squared plus 1. So the first term is x squared. So look, I'm going to list my terms out if you're asked to do that here. First we have x squared. The second term is just 1, okay, positive 1. And there are two terms, okay? So a term it can be just numerical with no variable at all. So each part is a term, each part separated by the addition or subtraction. In the trinomial example, right, that's below that, a trinomial, tri meaning 3, right, 3 terms. Okay, here's the first one I'm going to highlight. In the previous one, look, I'm going to highlight each term here, okay? Alright, so we have the negative 3x squared is our first term there. Positive 2x is the second term, and then, yeah, the number 1 is the third term. Okay, doke. Moving right along, let's take a look at the left side of the screen. Let's go over there, okay? We want to learn to take the opposite of. There's some things, some concepts that we need to go over, a few little things, to be able to be successful in this section, okay? Let's have a look at taking the opposite of, okay? Basically, when you're asked to take the opposite of something, what are you being asked to do, okay? Think about that. If I want to take the opposite of 3, okay, so let's say 3, the opposite of 3, I'm going to do this, right? I'm going to say I'm going the opposite of 3. Okay, let's write that down. Okay, if I wanted to put this in words, it would say the opposite of 3. Okay, and we had an example, like one of our first lectures where I did this, the opposite of, and I put like 2 to the 4th power here. Okay, so if I have this is not negative 2 to the 4th power. This is actually the opposite of 2 to the 4th power. So see, it's really different, and so you have to kind of get the words right. It helps to cross that language barrier to understand what to do. So this is the opposite of 2 to the 4th power. Okay, so how we do that is the 4 is only applied to this parentheses, right? If you would go back and look at that. So in other words, the opposite comes down. and then we do 2 to the 4th power. It gets carried out. And so the opposite of whatever that value is what you're looking for. So negative 16. Okay? So we have all that. That's fine and dandy. Let's look at the examples that I have written down here. Okay, so I want to find A in part A here. I want the opposite of negative 23x to the 4th power. So what is that? And if I wanted to write that out mathematically, it would look like this. The opposite of whatever the problem is. Just write it down as is, okay, in parentheses. So the opposite of that. What am I playing with? I'm just fooling with the signs because that's a monomial. I don't have to worry about anything but any distributing it to, multiple terms or anything. So 2 negatives, right? Negative times a negative. I'm going to get a positive value. So it's going to be positive 23x to the 4th. Easy enough, okay? So for the opposite of that, and by the way, I should not put an equal sign because that is not the equal sign. It's not equal to that. It's the opposite of, right? So I should put this, opposite of. Okay? So anyway, and I'll put an arrow. How about that? Okay. So at any rate, let's look at part B. Now, doing what we did up top, okay? So if you're asked to take the opposite, let me write in red exactly what I'm doing. So if I'm asked to find the opposite of this expression or this polynomial. Okay, so what do I do? So what I'm going to do is I'm going to put a negative sign outside of a set of parentheses, and inside the parentheses I'm going to put what I'm looking for, the opposite of. I'm going to insert this polynomial. Okay, and so let's do that. Let's put that value in. So we'll have, let's see, wait, get my bearings here. Negative 3x squared plus 2x plus 1. Alright, so take the opposite of, in other words, every term inside of the parentheses will become the opposite sign, right? If it's negative, it'll become positive. Or if it's plus, it'll become minus. However you want to think about it. You got to wrap it around your head some way, and everybody's different. So if you find a learning device, just however you choose to remember something like this, stick with it if it's correct, by the way. So each one of these items here in this trinomial, right? That's a trinomial because it has, what, 1, 2, 3 terms, right? So we'll have what? Positive 3x squared. By the way, you can put a little positive sign. Back in the days when we had positive signs, I'm just putting that for sake of showing you that this will become positive. Okay, and so plus 2x becomes minus 2x. Okay, or plus a negative 2x, however you want to say it, negative 1. Okay, every term, you have to be thorough, guys. A lot of times I'll see people doing this, and then they get down to that plus 1 down at the end, and it stays as a plus 1, and that's wrong, right? You have to be thorough. Every term becomes opposite sign. So just be very careful with that. Watch your signs, okay? So all this will help you to get better at watching your signs. Probably see me writing that a lot on y'all's papers too. But this is why, okay? All right. So here I'm going to just kind of look at a few things. I'm going to have various examples written down the page for you guys. You all, and so let me go and grab one more here. Let me go back up to that section here, adding and subtracting. Yeah. All right. What I want to do is just kind of remind you that basically when you're adding and subtracting these polynomials, what you're doing is combining like terms. That's all. You've got to keep it simple, okay, y'all? Make sure. Remember that saying, KISS, K-I-S-S, keep it simple, silly. I don't like the word stupid, so you won't hear me say that. But in this section, it goes beyond the just combining the like terms thing. And it starts talking about the degree of a polynomial. And this is kind of important because you are going to be dealing with second and third degree polynomials pretty soon. Let me go on there and get down to that. Okay, that's it. Okay, so basically in this class, you're going to deal mostly with the second degree, okay, polynomial. In a little while, very shortly, within the next couple of weeks, we're going to start looking at quadratic equations. And most of you have been exposed to this, know that quadratic equations have an x squared. A squared is the highest exponent in them, right, in those types of problems. Okay, so the degree of a term is the highest exponent. Okay, the degree of a polynomial. Okay, remember this. It's kind of important. Okay, you get that. If I ask you what is the degree of this polynomial, your answer comes from the exponent that's the largest or highest exponent. Okay, let me get that. So the highest exponent or power in a polynomial. So for example, let's state what the degree of the polynomial is. Okay, state the degree of these polynomials. Okay, and so I'm going to write this. Let's say negative 3x squared plus 2x minus 1. Now here's a trinomial, right? 3 terms. It's a trinomial. And we have a leading coefficient, right? The leading coefficient is negative 3. We have x squared, right? This is our first term, right? First term right here. Term 1, this is a term. Here's a term, by the way, separated by addition, subtraction. I'm going to get to the degree in a sec. And negative 1 is a term, by the way. The degree is taken from the highest exponent. We have a choice of this and this, right? Well, we choose the 2, right? So our degree is a second degree. So for A, we would say that this is a second degree polynomial. Okay? Okay, so knowing that, let's take a look at this one. How about B? Okay? And there's really not much of a trick to this, okay? This is something you've been dealing with, okay? So let's say we have something to this effect. Negative 3x plus 5 is equal to 1. Okay? Oh, sorry, equation. I didn't mean to make it an equation. I'll just make it this. Negative 3x plus 5. What is this? A monomial, binomial, trinomial, or polynomial? This is a binomial. Good job, okay? I don't know, I'm liking the negative 3s today for some reason. Here's my 2 terms, which means this is a binomial, right? By the way, I should label this first one a trinomial. Okay, so this got 2 terms. Here's the first term, second term, which makes this guy a binomial, right? This is 2. Okay, and so what degree is it? It's got the highest degree on any of the variables is understood because it's not actually pictured. It's 1. So we say this is a first degree polynomial. Okay? So it's first degree polynomial or binomial. Okay? Polynomial is fine. Okay? So, alrighty. So let's kind of look at some of these. We can add these and subtract these. I could say, for example, just for example, I could take the 2 in this example here and I can add them. Okay, so I'm going to make an example here on the right side, then I'll go to the one on the left, but let's go to the right then. And I'm going to say example here right underneath. Okay, give the sum of negative 3x squared plus 2x minus 1 and negative 3x plus 5. Okay, so what do we do here? What we're going to do is simply add them. And so, because of sum, right? The sum says to add, right? And when it's worded in this way, and that operation's listed in the front, right? And then you have the word and between the two things you're trying to apply it to. Wherever you see the word and is where you put that addition sign, or whatever it's going to be. Okay. So what I'm going to do is come down here and I'm going to write in parentheses. You really do want to get used to using some parentheses when you're creating the problem if it's written like this. If you have to translate it into an algebraic expression. Kind of don't be afraid to put each individual polynomial in a set of parentheses. So we want the sum of this and that, right? Okay. And so here's what that looks like. Okay, so now we're going to simply, it's just addition. Technically, you don't need the parentheses because it's addition between the two. So we're going to go straight into combining like terms. Let me put my square on my x. Yes, I did forget it. I got it now. Oh, no, it's not a square. What am I doing? I'm sorry, that's from the second one. So we got it right. Yeah, negative 3x plus 5, right? Negative 3x squared plus 2x minus 1. I can make sure I copied it correctly. Okay, so next step is to combine the like terms. What we're going to do is we're going to start from the highest exponent, okay? Because everything about the variable ending has to match. Okay? And so what I'll do is I'll trace these out in red as I'm taking care of them. So this guy, does this one have a friend with an x squared ending? No. No other thing has a square x squared ending. So I'm just going to take it down to the next step. Now, x terms, okay, if there's nothing on the x as far as an exponent, it's understood that it's a 1 exponent, right? So the first power. And so we're going to combine those two things, the coefficients, plus 2 and minus 3. That would be what? Negative 1, correct? X. Then tack on your ending. The x is there. So we'll have minus 1x or just minus x. Okay? And now negative 1 and plus 5. So, or you can say 5 minus 1 if you like to do that. So we'll have plus 4. And we're done. Voila. C'est fini. Okie dokie. And here is... it's in descending order. We want to make sure we have each of these answers simplified, right? We want to make sure it's completely simplified. And so far, as of now, simplified means descending order. Okay? So give answer in descending order, or what we call now standard form of a polynomial. Okay? So let's have a note about that. So here, let's kind of look up here at the top, and I'm going to show you something now. Descending order would look something like this, and this is like the basic format, where A, B, and C, or basic and D, if you want to keep going there, real numbers, okay? So we might have A, X to the M, okay, and M is the degree, okay, M degree. Okay, and so we would have a countdown, X to the next one would be x to the m minus 1, okay? And then next we would have minus another, right? Etc. Okay? So this is one way you will see it pictured, okay? Another way you could see this type of thing being given to people in textbooks would be this, in this manner. It could look like this, okay? It would be put in the form of a trinomial. It could be this, ax squared plus bx plus c, which is just a constant, okay? Conveniently, c is constant, okay? Notice our highest exponent is first, and then we count down, okay? Alright, and so you'll see me doing that in these problems, and if you go back through the other videos, you'll notice I've put them in descending order previously, unless there were two terms and there was reason for it. Okay, at any rate, let's subtract these two here. Let's go to the problem down below where I just wrote that, okay? So let's subtract 5x squared plus 3x minus 4 from 3x squared minus 5x plus 4. And let's see what happens here. Okay, and let's give a little room so we can work. Okay, so back to the pen. Okay, so we're going to take 5x squared. Oh, I'm sorry, what are we going to do? We're going to subtract this guy from this one. So the second one is written first. So we have 3x squared minus 5x plus 4. And from that, we want to subtract 5x squared plus 3x minus 4. Now we're subtracting, so you do need these parentheses now, and be very careful with these signs, okay? Because we are about to take the opposite of three things. So let's write it out. So here's what your problem initially will look like, okay? So let's go ahead and take care of that negative, okay? So let's go here first, okay? So we're going to 1, 2, 3 terms, right, inside the parentheses that will become opposite signed. Okay? And so let's bring down the first polynomial. Once we do this distribution of the negative, we don't need our parentheses anymore, okay? So you can kind of disregard the parentheses now in this step. Here's why. Because we're taking the opposite of positive 5x squared, which will make it minus 5x squared. We're going to take the opposite of plus 3x, it becomes minus 3x. Taking the opposite of negative 4 becomes plus 4. Okay, is that what you got? Good job. Okay, so each sign inside the parentheses, right, each sign went to opposite. Okay, so there you go. These guys changed. That's the only thing that changed, right? Now we have no parentheses, nothing else to handle except for combining like terms. I want you to notice a pattern here, you guys. When you distribute, right after distributing, 99.9% of the time, I'm going to combine like terms. So you distribute, then you combine like terms. Get used to, like, glue those two phrases together forevermore, and you can't go wrong. You'll do very well. Distribute, then combine like terms. Now, what's the highest degree? What's the highest exponent here? Is a 2, right? So let's begin with that. We'll combine anything with an x squared on the end of it. Okay? So in this case, we have the 3x squared. Okay? This guy, and we have the minus 5x squared. Okay? Which would give us negative 2x squared. Okay? Okay, and then after that we have minus 5x and minus 3x, which would give me negative 8x. Okay, and finally we have plus 4 and plus 4, which will give me plus 8. So this guy's done. Alright. Alright. Part of this section is when we're adding and subtracting fractions that have variables in there. Their numerator or denominators contain polynomials. Okay? So right here we need a common denominator or an LCM of 6, 4, and 3. Okay? 6, 4, and 3. Let's take a look at that. On the right side, LCM, I'm going to put equals, so we'll come up with that, and we have 6, 4, and 3. 3 is prime, right? That's just 1 and 3, so I'm done with that one. Prime factors of 4 would be 2 and 2. Okay? So 2 dot times 2. And 6 is just going to be 2 times 3. Well, we have two factors, a 2 and a 3, right, that we need to take some amount of time. Okay, in each individual factorization, what's the most, in each scenario, which the most 2 was ever mentioned? If you said in the 4, or let's say twice, you're correct. So for 2, the factors of 2, I'm going to take that into my factors of the least common multiple twice. In each individual case, 3 is mentioned the most, only once. So we will have only one 3 in our LCM. Multiply that up and we have 4 times 3 or 12 for our LCM. Let's keep going. So with our LCM or our common denominator of 12, what I've done here is I set up 3 fractions because our original problem had 3. I call them dummy fractions. So the 12 is kind of a wish list sort of step. Okay? So it's going to be equivalent when I'm done with it. I'm painting the picture right now. So let's take a look at the first fraction, the one with the 6 in the denominator, okay? Answer this for me. 6 times what was 12? Okay, so that's what you want to ask yourself. What times 6 was 12? Okay, 6 times 2 was 12, right? So I must have multiplied a 2 times the 6 to get the 12. So what I multiplied in the denominator is what I want to multiply into that numerator. Why? Because that's a form of 1. 2 over 2, and look, I can put that over here in the front, actually, in this, of the 6, and it'd be better for you to see. 2 times 6, right, would give me the 12. Notice what is a number over itself. If I'm multiplying 2 over 2, right, well, a number times itself is just 1. And whenever I multiply 1 times anything, it stays, the value will stay the same. So I'm not, it's like empty calories or free points, and when you're on a diet, you know, you can multiply 1 or divide 1 as many times as you want to, and you're not going to change the value of your answer. But it can change the look of it, right? If we want a common denominator, that's quite handy. Okay, so in our numerator we'll have 2 times 5, which is now new numerator is going to be 10, right? And then x minus 1 is back there. Well, you can just leave it like that for now. We don't have to distribute just yet. Just kind of leave that attached to the coefficients on the front. The coefficient of 5, it'll get distributed soon enough. Let's just leave it like that for now. Let's look at the 4, okay? So doing the same kind of type of thinking on that. 4 times what gave us 12? 4 times 3, right? So if I multiplied in a 3 in that denominator, I have to do the same thing up top to keep the 1 balance of multiplying in a 1, that concept we just spoke about. So I got my 12, like 3 times 4 is 12. That's all good. Now 3 times 2 in my numerator is going to be what? The new coefficient on the front of that parenthesis will be 6 times 3x minus 4. Okay? And now, finally, 3 times what was 12? 3 times 4, right? Well, if that's the case, then 4 is also needing to be multiplied into my numerator to balance it out, which would leave us what in the numerator? An 8x. Okay, so we have 8x, oops, in our new numerator here. Okay, so now what we can do, since we have our common denominator, we can go another step, and I can just kind of marry everybody. I'm going to put everything over 12. Okay, and I can do the distributions and do this in the same step. So first off, I'm going to do the 10 goes into x minus 1. Okay, so distribute 10. And we'll have 10x minus 10. Longer fraction bar. Okay, now we'll distribute 6, or what? Is it just 6? We'll distribute negative 6, right? See that minus sign here? Watch, this guy. You got to be careful because you can translate that into this, plus negative 6, okay? If it helps you. Okay? So that is what that's what happened there, okay? So kind of be careful with that. So what we had before was minus 6, and what we did was we changed it to plus a negative, right? Subtraction and plus the opposites. Plus a negative is the same thing. This will make it easier when you're distributing and you're going to have to deal with distributing a negative value. Okay? It helps you keep track. So negative 6 times 3x, okay, minus 18x. And let me kind of go back to my color. Okay, so negative 18x. And negative 6 times negative 4 is positive 24. Careful with that, and then just bring over your 8x. We don't have to do anything else with that. So now in that numerator, we have to clean up. We have just distributed, and we said next would be combine like terms. Remember, I talked about that earlier. Distribute, combine like terms. So let's go down a step. The highest exponent is just 1, right? It's linear. It's x. And I'm talking about just in the numerator. So we're going to start there. We're going to start with our x terms, okay? So here we have what? 10x minus 18x, okay, and plus 8x. Alrighty. So let's combine the coefficients and tack on the variable ending. 10 minus 18 is negative 8, plus 8 is what? So what do we have? We have what? 10x. Let's go through that again. Yes, your ears are not fooling you. So we'll have 10, positive 10, minus 18. That gives us negative 8. Then plus 8x. This is all the x terms, right? That's going to cancel, right? So these guys are gone. No x terms left. So now I only have to go to the constants, negative 10 and plus 24. That's all I have left, really. I'm going to go ahead and rewrite it just to show you. Over 12. Okay. 24 minus 10 is what? 14. Over 12. Okay, or what? 7, 6. And that is reduced improper fraction form. That is fine. This would be simplified. A lot of people ask me, when do I use a mixed number or when do I have to convert it into a decimal? Okay, that depends on the context of the problem oftentimes. You may get a different answer from another professor, but honestly, it depends on the context of the problem and what grade you're in or who's asking the problem. It all boils down to know what you're being asked for. You know, what's the end game? Keep your eye on the end game, and you'll be able to answer that for yourself. Okay, next part. Let's talk about the rules of exponents. Oh, joy. Almost done, though. We're not going to be here too much longer today. Okay, so here are my rules of exponents, okay? Now, you've had these before, okay, in the beginning of this semester. Now, again, I'm going to say we're just using them in a different context. So like I said before, a lot of the stuff you've done before, you know how to do this stuff. We are just kind of doing it, we're using a different, I guess it's serving a different purpose, and like I said, it's in a different context. Better way to say it. Alright, so let's kind of review these really quickly. I'll give you one little example with each thing. Okay, so rule 1. We're going to multiply straight across. These are exponential forms. Multiplying straight across. And we have like bases, okay? So what am I talking about? I have multiplication of exponential forms and my bases match. So it's x raised times x raised to some other power. And so what do we do with those exponents? We add them, okay? So that's easy enough, right? So really quickly, if we have 2 to the third power times, say 2 to the x power. What's up with that? Well, the long and short of it is the 2's match. My bases match. So I'm going to add my exponents. So I'll have 2, again, the same base, and a single exponent where we add our exponents. So I'll have 3 plus x as my new exponent. Okay, rule 2. Let's go to the right there. I am dividing exponential forms now, and again, my bases match, okay? See that? The bases match. What do I do with them? What's happening here should actually, another picture of this statement would look like this. I could have x to the a power divided by, right, division symbol, x to the b power, okay? And if a is larger, okay, this can go in either direction. I could bring the a down and it would be b minus a, by the way, if I need to, okay? Or it can be that maybe b is the smaller value, and it would be, if I move this guy upstairs, right, if I cross the fraction bar with whichever exponential form, it does negate or takes the opposite of whatever that power is, okay? So watch what really is happening here. I'm going to have x to the a, that was in my numerator, right? This is going to become 1, so it's still there. The denominator is still there. Now I'm going to have x to the negative b in the numerator, right? That's what just happened, right? We know that rule. If we cross over, it becomes minus subtraction in the exponent. Okay, so, and we know the very first rule that we just had a look at, right? We know that if I multiply straight across and my bases match, I'm going to add my exponents, right? Remember that? Rule 1, we just looked at it. So now I will have x to the a plus a negative b, or what? A minus b. So that's how we get that one, okay? So this is kind of like a little proof of that rule 2 there. So here's a little example, some ways we could look at that. Okay, so example would be this. Let's say I have 2 to the 5th power over 2 to the 3rd power. Okay, well, if I need to have, for simple form, right, by the way, for something to be completely simplified, you do not want to have negative exponents. So no negative exponents are allowed to be left over in any of your answers. Remember that. So the smaller number we would like to go be subtracted from the larger, right? So we want to cross the 3 exponent over. I want to take this value in the denominator and bring it upstairs, right? So we'll have 2 to the 5th minus 3rd power, right? So that'll be what? 2 squared. And of course, ultimately a 4 is your answer. Okay, so there's that. I'm going to give you one more like this, and then I'm going to erase these. So let's just say, okay, this is one example. Here's another example. Okay, separate them out. So for example, if I have, okay, 2y to the 5th power, okay, over y to the 8th power. Okay, and that's an 8 exponent. Let me put it a little bit closer to the 8. The y is usually. Wait, come back. Hold on, my pen is messing up. Alright, so 8 is actually the exponent of the y. Okay, so now, look at that. That 5 exponent of 5 is smaller than 8. Well, I would like that to get subtracted from 8. Well, it's fine. This rule works in either direction, okay? If we want to cross the 5 exponent down to the denominator, right? Here's what happens, okay? That 2 is really not even involved in the drama of the y's, okay? So it just gets kind of carried along. Leave it where it is. Don't try to change it. Okay? All right, so 2. Okay, what happens when you cross over that 5, by that exponential form, the y to the 5th, is there's going to be a 1 that's left over. Okay, so that's going to be 2 times 1. I'm just reminding you that there is a 1 that's left over wherever the previous tenant lived, so to speak. Okay, so here we have 8 minus 5. And so the final answer is going to be 2 over y to the 3rd power. Okay? So that's how that kind of gets handled. We'll look at some more of those, okay, in a bit. Let's go to that third example quickly. Okay? Alright, so what? I'm raising a power to a power in the third rule here. You multiply. It's very simple. If you're raising a power to a power, multiply the exponents, right? This is what I mean by raising a power to power. Here's an exponential form being raised to another exponent. Okay? So the power of A is being raised to the power of B. Power to a power rule, okay? And we multiply, okay? All right, a similar thing happens for 4. And what I'm going to do is the examples I'm going to show you are going to kind of, first I'll do one that looks like 3 or 4, and then it'll probably look like both of them. Number 4, a lot of people tend to call it distribution, but it's not. You're not distributing the B. Every term inside the parentheses is being raised to the B power. Okay? As long as it's multiplication inside the parentheses, okay? Let me make sure you see in what I'm talking about. If it's multiplied, if you have factors, okay, inside parentheses, this is how this rule works, only on multiplication. If you have addition inside there, it's not the same rule. Not going to work. So if you have factors that separate by multiplication, right? Each factor inside the parentheses will get raised to the B power. Okay, so an example for 3 and 4 here. Okay, so let's go this route. Okay, example for this one. If I have negative 3x squared y to the 3rd power, and let's say I want to raise this to the 4th power. Okay? What's going to happen? Notice example 4 is going to answer that for us. Since I have all multiplied items inside the parentheses, each factor, each part of the multiplication is going to get raised to that outside power of 4. Let me write that out for you. Okay? Here's what that looks like, what I just said there. So we'll have negative 3 raised to the 4th power times x squared, in parentheses, gets raised to the 4th power times y cubed, also raised to the 4th power. Okay, so each item, each factor gets raised to whatever that outside power is. And notice I didn't try to change any of the factors independently. I just left them like they were. I just kind of separated it out like that. And now, after you've sussed what you've thought it out correctly, like I just wrote, then you go and simplify each one. So negative 3 to the 4th power. What is that? That's, first of all, it's going to be positive, right? Because any negative value raised to an even exponent, that's going to cancel, all the negatives cancel themselves out. So we'll have, what, 81 for that, okay? Positive 81. And now, raising a power to another power, rule 3, what happens in rule 3? Raising a power to a power, you multiply the exponents. So now we'll have, next to 81, we'll have x to the 8th power, right, multiply, times, or you don't have to put the times symbol, it's understood. 3 times 4 is 12. And there's your answer for that one. Okay, so now let's take a look at example 5. Rule 5. All right. Now for rule 5, what we're doing in rule 5 is we are learning to write our exponential forms as radicals. Radical form, we're learning to put that into exponential form. So let me write that out, okay? So what this is I'm going to write this right on top, okay? We have first this guy. The first thing, x to the a over b, is exponential form, right? Exponent form. Okay. Exponential form. Okay. And let's see. And put that real little right here, form. And then what we have here with the radical symbol, the b root of x to the a power, this is your radical form. Anything with the radical symbol. A radical symbol is a square root or nth root sign, okay? Call that radical form. Thing is, rule 5, let me explain it to you over here. And what I'm going to do, let's see, make a little room here. Okay, That's fine. So an example for number 5, okay? If you have, and I'm going to go from radical form to exponent form, okay? Let's say I have the cubed root of y to the 5th power. Okay, think of root, okay, that root symbol, the number that we call the 3 is the index, right? Let's remind ourselves of that. Okay, the number here is called the index. Just to remind you of what's what there. And of course, we call the 5 there our exponent or a power, right? Okay? You don't need me to label that. But the index is the root, and which is, if you had to choose between the top or the bottom of a fraction, a root would be underground, right? So if you want to remember where the 3 goes, it's the root of the fraction, right? The denominator. So to put this into fraction form, I'm going to have y as my base, right? And I'm going to have some fraction, right? So 3 will be the denominator of that fraction, or in that formula where b is there. Okay? And then 5 is the power, right? That's above ground in terms of whether it's a root or a leaf. Oh, never mind. Okay, if you weren't following that analogy, it's okay. So at any rate, so 5/3 as my exponent is going to be the cubed root of y to the 5th. Okay? Incidentally, this is also the same as if you'd written the radical this way, cubed root of y raised to the 5th power. See, it could be written like this too. It's what is going on with those two different looking radical forms is in the first format, when I have the 5th powers inside the radical with the y, what's happening here is that's what's getting done first, is that 5 is going to be carried out first, the power, the exponent, and then they go for the root. In the second way that I wrote it, the cubed root of y is what's getting done first, okay? So this is what's getting done first in this way, in this version. At any rate, they should end up at the same number. It's the same thing, okay? All right, and what I have next is number 6. Okay, number 6, when I have this rule here, this is basically the same thing I did earlier when I was talking about number 2 there. It's the rule that makes part 2, or rule 2, possible. It's just telling you if you have a negative exponent, you can't leave it as an answer, right? We have to make all our exponents positive. Okay, so here's how. We cross over that fraction bar. And look, remember, if it's written like this, like x to the negative a, remember that it's, even though you don't see it, you have a denominator of 1 there, okay? So your fraction bar is there, it's just implied. Okay, so an example of this rule. And this, by the way, incidentally, rule 6 goes in both directions. In other words, if you have this, if I have, let's say I have 1 over y to the negative b. Okay, well, this is not simplified, right? I would need to make that negative b positive, and I do that by crossing to the numerator, and the b becomes positive. Okay, and of course b, in this case, similar to the previous rule, you want to go ahead and have a disclaimer of if y cannot be 0. Okay. Okay, and then number 7 is just saying anything I put a 0 exponent on is going to be 1. In other words, if I raise anything to the 0 power, it's always going to be 1. A small example for that would be if I raise let's see, 893, 20, let's see, 1,543. If I raise this number, 2,893,020,543, to the 0 power, what is the answer? 1. Always. Anything. I can raise any number to the 0 power, right? As long as it's not 0. Hint, hint. Remember that. Okay, anything to the 0 power is 1. Okay? I said it again, and I'm going to say it again and again. Many times before the semester is over, just not now. Let's move on. God, y'all are so silly. Okay, almost done now. Okay, so let's just go ahead and use our exponent rules to distribute negative 2mc. Okay? Let's get this big boy done, and we're almost home free. Okay? What I'm going to do, you guys, to help you out is I am going to write out the two multiplications that are involved in distributing this value, okay? So here we go. Okay, so negative 2mc is going to be multiplied by each term inside the sets of parentheses. So negative 3m squared c cubed first, right? Then we distribute it to 5mc. You want to go to every term inside. Be careful with that and distribute thoroughly. And watch two things, your signs, and now watch your exponents. Careful with the exponent rules. Let's do these terms one at a time. We'll have negative 2 times negative 3 is positive 6. Okay, we have m to the first power and m to the second power. Straight across, the bases match. You'll add the exponents. So we'll have 1 plus 2, 3. Then we have c to the first power, c to the third power, which becomes c to the fourth power. Okay, in the second term, negative 2mc is going to be multiplied times 5mc. Now, plus negative. Now, this whole term is going to become subtraction, or minus, or negative, however you want to look at it. Now, let's just look at the numbers. 2 times 5, 10. M times m squared, or 1 plus 1, is going to be my new exponent, m to the second power. And c's, they both have implied 1, so we have 1 plus 1 for the c as well, for the new exponent. Okay, now look at the variable endings closely. We have m cubed, c to the fourth, and m squared and c squared. These variable endings do not match. So this is the done. We're done with this. This is as simplified as it's going to get. So answer is done. Safe and neat. Okay, let's go down to see what we have waiting for us, if anything, okay? Let's look at this one here. Okay, 12a to the fifth power b cubed c to the fourth over 4a cubed b c squared. That b in the denominator is b to the first power, right? If you want to, you can write in a 1. It's implied, but if you want to help, if you want that written there, a 1 on the exponent, on the variable, to help you remember the rule correctly, it's fine. You can put it in there. Some of these problems may be written with the variables written very closely as well. So if you need to rewrite your problem and give yourself a little space for each thing, you can do that. That's fine. Let's go ahead and take care of the numerical, the coefficients first. Of course, 4 goes in itself once, into 12 3 times. Let's go ahead and write a fraction bar. We're just going to kind of use this first fraction bar as like a scratch work fraction bar. We'll clean it up in the next step. So we end up with a 3 here. Let's look at the a's. A to the fifth power and over a to the third power. Remember, the smaller exponent needs to go up and to be subtracted from the larger exponent. Right? So we want this guy to come up here and be subtracted from the 5. Okay? So I'm going to end up with a in my numerator, a to the 5 minus 3, which is 2. Okay. B cubed over b to the first power. The smaller exponent is going to cancel. It's going to go up to where the larger one is and be subtracted from it. So we'll have b to the second power here as well. Similarly, the c squared will go on up to be subtracted from the 4. And we'll have b to the second power. What happens is, if everything moves and you have nothing left on either the numerator or the denominator, remember there is a 1 there. Okay, I just want to show you that. Because if I have a problem like what I'm about to write out, here's what's going to happen there. Okay, so let's say we have this. Maybe I have 2x, let's say negative 2, this is my exponent, y, over, let's have 4x squared y. Okay, so what about this problem? Okay, let's do, here's an example, and so this is going to be my next example. What about this problem? Okay, so let's take a look. Of course, we can go to the coefficients first. 2 cancels with itself, right? It gives me a 1 there. 2 goes into 4 twice, leaving me with a 2 in my denominator for my numerical part. Now, out of negative 2 and positive 2, negative 2 is smaller, right? So remember, the smaller one travels to the other side of the fraction bar and gets subtracted. Careful here, though. What are you subtracting, okay? You have a negative 2 that's going to get subtracted from positive 2. So if you kind of like come out to the side over here, you're going to end up with it, you're going to have as your exponent 2 minus a negative 2, which is basically what? It's going to be 2 plus 2. So I just kind of want to remind you of that. Be careful. This is going to cancel, and that exponent is going to be subtracted. So minus a negative 2 gets tacked onto that x in the denominator. So what is that going to be? X to the 2 plus 2, right? Or x to the 4th power. Okay? And so what happens with my y's? Y goes into itself once and into itself once. Okay? Another way to look at this, though, if I want to stick to the rule I was just using, I put 1s on there. Let's say I want to take this guy down to the denominator and subtract and do the rule, right? Use the rule. What am I going to have? I'm going to have y to the 1 minus 1. Okay? Look, I'll take this another step for you just to show you. 1 is left in my numerator, and I'll have, what happens to this guy? This is going to be y to the 0, which is just 1. Anything, we said earlier, to the 0 power is 1, right? It's my ugly big fat Sesame Street 1, sorry. Okay, so 1 over 2 x to the 4th power is my answer. So there you go. We had some groovy little rules that I showed you in that one. We may be a little long-winded on that one, but I wanted to kind of get that one out there because it has a lot of good stuff in it. And some things you're going to be using too. So be safe with your signs and your exponents now, okay? The last problem I want to take a look at is over there on the right. Okay? This is going to be the last one today for this lecture. I want to find the value of question mark that makes these statements true. Remember your rules, okay? Now, let's take a look, okay? Let's say I'm going to go ahead and write out m to the question mark, okay? It's going to get distributed into x to the, m, I'm saying, m to the 4th plus 2m cubed. Let's go ahead and take it out a step, okay? What are we doing, okay? When we multiply, let's kind of come here on the side. Hold on. I'm going to write a small example on the side in red, okay? Sidebar or side example. Just to kind of remind you, to take you through the steps that usually you would be doing. So if I have x squared times x cubed plus 2x, that's good, x is fine. Let's say if I had something like this, for example, okay, I'll just change the exponents just to kind of make it something different, but essentially the rules are the same. What are you doing when you distribute this x squared to the x cubed? What happens to the exponents? What's going on is this. Okay, let me write out these multiplications so you can kind of think about what rule to use. You're going to have x squared times x cubed plus x squared times 2x. Okay, let's look at the first term here, okay? The x squared times x cubed. We have matching bases. We're multiplying straight across, right? So what we're going to have is addition of the exponents. So we're going to have x to the 2 plus 3, right? Or x to the 5th. Now in the second one, we're going to have the 2's got to come up to the front. And we have x squared times x to the 1, or what? X to the 2 plus 1. So we're adding the exponents, right, to get to the end of x to the 5th plus 2x cubed. Keep that in mind. What's going to happen? Look at what we want the end game to be. Let's go back to our problem that we're working on. The end game is an exponent of 6 for the first term and an exponent of 5 for the second term. Okay, and of course the coefficient of 2. Well, what are we distributing? We have an m to we don't know what power. That's the question. Okay, let's take it one term at a time, okay? What do we want to happen, okay? So let me get rid of that, what I wrote so far. Maybe there's a better way to write this. What do we want to happen? That's one way to say it, okay? We want, essentially, when we distribute this guy, going to first get distributed here, so we'll have what? M to the question mark. We can call it x. M to the x plus 4 is basically what's going to happen, right? And what will x plus 4 end up being? It's going to end up as 6, right? Okay, so watch. Okay, let me write the next one out. We're going to end up having what? 2 to the m, what? X plus 3. Which we want that one to be 5, right? Okay, let's take the first one now, okay? So we want what plus 4 to be 6, right? Remember, we want it to be m to the 6, right? And we want this one to be 2m to the 5th. So what? Let me write this on the side to make it perfectly clear. So we're going to take this guy, and we're going to come out to the side, and we want x, excuse me, we want x plus 4 to be 6, right? So solve for x. Subtract 4 from both sides. You're going to end up with 2. So we want there to be a 2 on that m. Let's verify that with the second one, okay? So we want this exponent and this exponent to end up being the same thing, right? We want x plus 3 to add up to be 5, right? That's our wish list. So we're going to have x plus 3 is equal to 5. Subtract 3 from both sides, and x is equal to 2. Voila, they agree. So we wish to have, instead of question mark, we want to have a 2.
C'est fini. Bon jeu.